On a clear spring day in 2020, I hope to be staring at a rocket on a launch pad and listening to a countdown. The passenger atop that rocket will be a robotic spacecraft that, among other things, will represent one of the most advanced and extraordinary technological achievements ever created by humans. This passenger will endure a harsh 8-year journey en route to its final destination, in orbit around Europa, the 6th moon of Jupiter. Its goal will be nothing less than to explore the habitability of an ocean that may contain 2 to 3 times the volume of all the liquid water on Earth. Europa's ocean, like our own, has existed for much of the history of the solar system. It's an ocean that could answer one of the oldest questions humans have ever asked. Is there life beyond Earth? This mission marks the beginning of a new age in exploration. For much of human history, we have been explorers of continents, examiners of rocks and regions ripe for habitation, the culmination being the heroic age of Antarctic exploration, and the capstone being our flags and footprints on the surface of the moon. But in the decades and centuries to come, exploration, both human and robotic, will increasingly focus on the ocean depths, of both our own ocean and the subsurface oceans believed to exist on at least 5 moons of the outer solar system. Jupiter's Europa, Ganymede, and Callisto, and Saturn's Titan and Enceladus. The total volume of liquid water on those worlds is estimated to be more than 100 times the volume of liquid water on Earth. The motivation for the coming age of ocean exploration will be to better understand the delicate balance of Earth's habitability, while simultaneously expanding our understanding of habitability, and possibly inhabitants on distant worlds in our solar system and beyond. It is an endeavor that will benefit greatly from both private entrepreneurs and inventors and large-scale initiatives by NASA and the National Science Foundation. NASA envisions autonomous vehicles that will melt through the surface ice and explore those distant oceans with a very high degree of artificial intelligence. Such missions are many decades away from the launch pad, but their technological precursors, some of which are funded by the NSF and others by entrepreneurs, are currently exploring Earth's ocean, discovering bizarre life forms deep beneath the surface. But beyond the prospect of liquid water, what makes ocean worlds like Europa compelling places for astrobiology? Despite considerable evidence to the contrary, Earth was not a particularly good place for life to arise. The main ingredients for life as we know it are a lot easier to find farther out in the solar system. The reason goes back to the earliest days of planet formation. With the Sun at the center, the primordial disk of gas and dust differentiated as a result of heat, gravity, and solar wind. Heavy materials condensed and accreted into the planets of the inner solar system, and lighter materials eventually froze out in the cold outer regions. Water, carbon dioxide, methane, ammonia, and nitrogen gas are all light, volatile compounds that were largely baked out of the inner solar system and condensed into the gas giant planets and their moons. Those compounds are the raw materials of life. The fact that Earth has a large ocean has long been a mystery to planetary scientists. Given Earth's location and formation history, it should be a considerably drier, less volatile-rich world. The generally agreed-upon solution to this puzzle is that after the epoch of planet formation, comets impacting Earth delivered water and other volatiles here. Indeed, it may be that for each glass of water you drink, roughly half comes from comets. Some of the evidence for this hypothesis was uncovered by studies of hydrogen isotopes in water, isotopes that serve as fingerprints identifying the water's original source. Much of our scientific interest in comets stems from a desire to better understand the role those objects played in making Earth a habitable world. So the ice-covered ocean worlds of the outer solar system likely harbor liquid water and the raw materials for life. Much of the water in the outer solar system is ice, but some is liquid. On Europa, for example, we have good evidence for a global liquid water ocean some 100 kilometers deep, lying beneath an ice shell perhaps no more than 20 kilometers thick. That's a tremendous amount of water, and if we've learned anything about life on Earth, it's that where you find liquid water, you generally find life.